Did you know that the machines powering global industry, transportation, and our electrical grids consume energy equivalent to building thousands of the Great Pyramids of Giza every single day? This hidden power isn't just about raw force. It's delivered by some of the most massive and awe-inspiring engines ever conceived. From the dawn of the industrial age to today's modern world, engineers have chased the dream of bigger, stronger, more efficient powerhouses. Get ready to take a journey through history and dive into the incredible scale and engineering genius behind the world's most powerful and giant engines. Our journey begins in the age of steam, a time when raw pressure was king. Picture the late 18th and 19th centuries. The engines that drove the Industrial Revolution weren't small. Early steam engines were clunky, but they quickly grew into colossal machines. Think of the beam engines, towering structures in factories and mines, with massive beams rocking back and forth, driving pumps and machinery with the power of boiling water. These were mechanical giants, their sheer physical size necessary to contain the immense forces of steam pressure. As steam technology evolved, so did the engine's power and scale. Reciprocating steam engines became the heartbeat of global shipping. Imagine the engine room of a massive early 20th century ocean liner. You'd see multi-cylinder engines with pistons the size of trash cans, connecting rods like tree trunks, and crankshafts so large they needed multiple men just to inspect them. These engines were colossal, spanning multiple decks, their rhythmic pounding driving propellers powerful enough to push thousands of tons across vast oceans. They were engineering marvels of immense moving parts, powered by the simple expansion of steam. While steam dominated for a long time, the early 20th century saw the rise of a new kind of giant, the diesel engine. Unlike external combustion steam engines, diesels burn fuel directly inside the cylinder. This was a game changer for efficiency and power density. Early large diesels quickly found their way into ships and power generation. Imagine a large, slow-speed marine diesel engine built for a cargo ship. These engines are absolutely colossal, often standing as tall as a multi-story building and stretching the length of a gymnasium. Modern marine diesel engines, like some built by Wärtsilä or MAN, are among the largest machines on Earth. The biggest ones have multiple cylinders, each with a bore, diameter. Wider than a grown man is tall. Their crankshafts are multi-piece monsters, weighing hundreds of tons. These engines produce over 100,000 horsepower, enough to move supertankers and container ships carrying 20,000 containers. The sheer scale of these components, pistons, connecting rods, crankshafts, cylinder blocks, is mind-blowing, a testament to achieving immense power and torque from internal combustion. As technology advanced further, especially in the mid-20th century, the gas turbine emerged as another powerhouse. Unlike diesels or steam engines that use pistons, gas turbines burn fuel to create hot gas that spins a turbine wheel, similar to a jet engine. While aircraft engines are built for power to weight, industrial and power generation gas turbines are built for sheer output. Imagine a power plant gas turbine the size of a bus or even a small house. Modern industrial gas turbines, like those in GE's H-class, are engineering marvels generating hundreds of thousands of kilowatts, enough electricity for hundreds of thousands of homes from a single unit. They involve incredibly complex internal components, spinning at thousands of revolutions per minute in temperatures hotter than molten lava. Their power output, efficiency, and relative compactness compared to older technologies make them the giants of modern electrical generation. Some large ships, including cruise liners, also use gas turbines for their combination of power and smoother operation. Comparing these generations of giants is fascinating. Steam engines were the pioneers, relying on brute pressure and massive physical structures. Diesel engines brought efficiency and incredible low-end torque, dominating heavy transport. Gas turbines delivered immense power density and high-speed rotation, becoming the backbone of modern power grids and high-speed applications. Each technology pushed the boundaries of materials, science, and engineering to harness energy on an ever-increasing scale. These engines, whether the visible, rhythmic giants of the steam age or the humming complex powerhouses of today, are the unseen heart of the modern world. They drive global trade across oceans, power the trains that move goods and people, generate the electricity that lights our cities and runs our factories, and fuel the massive pumps and machinery of heavy industry. They are a testament to humanity's relentless drive to build bigger, stronger, and more powerful machines. So, the next time you see a massive cargo ship, a powerful train, or simply flip a light switch, take a moment to remember the incredible journey through history and the engineering genius behind the world's most powerful and giant engines. From towering steam engines and colossal marine diesels to blazing hot gas turbines, they are the hidden giants that built our modern world. What era or type of giant engine fascinates you the most? Let us know in the comments. Every year, the world produces over 60 million metric tons of aluminum, and a significant portion of this metal is turned into key parts for automotive engines. Did you know that over 75% of modern engines have aluminum cylinder heads? This choice isn't accidental. Lightness, strength, and the ability to withstand high temperatures make aluminum an ideal material. But what happens behind the scenes in the production of these critical components? How are tons of metal transformed into complex, high-precision parts? Today, we're diving into the fascinating world of industrial manufacturing, and we'll show you the whole journey, from raw material to finished cylinder head. Cylinder heads are most often made from two primary types of materials: aluminum alloys and cast iron. As of 2025, over 75% of modern automotive engines are equipped with aluminum heads, due to their lightness, good thermal conductivity, and the reduction of the overall weight of the power unit. One aluminum cylinder head assembly weighs on average between 10 and 20 pounds, whereas cast iron equivalents can exceed 40 pounds. Aluminum for such parts isn't just metal, it's a high-quality alloy, for instance with added magnesium or copper, which provides strength at high temperatures. The main suppliers of aluminum are countries like the People's Republic of China, which provides over 60 million metric tons annually, and India. In the United States, the majority of aluminum raw material is supplied by sea transport in the form of ingots or granules, which are subsequently remelted at local foundries. One standard 20-foot container holds up to 48,000 pounds of aluminum ingots, which is enough to produce over 1,000 heads. Cast iron, although less popular in new engines, is still actively used in heavy machinery and trucks due to its durability. Its production requires components: iron ore, coke, and limestone. The United States partially extracts ore itself, but imports a significant portion from Canada and Brazil. Rail transport is used. One typical train with raw materials can deliver 10,000 to 15,000 tons of iron ore to metallurgical plants. After the materials arrive at the facility, they undergo cleaning, sorting, and melting. For example, casting one cylinder head requires up to 22 pounds of aluminum, and the cycle from melting to cooling takes about 90 minutes. This is just the beginning of the production chain, in which each part goes through dozens of stages before being assembled onto an engine. Aluminum ingots or granules arrive at the plant in sealed containers. They are unloaded onto special platforms with automated cranes and delivered to the melting shop. Before melting, the aluminum is cleaned of impurities and moisture to avoid porosity in the finished casting. For this, the raw material is placed on vibrating tables with metal detectors or sorting conveyors. Robots or operators manually or mechanically reject unsuitable material. This is how contaminants, paint, oil, plastic, and shavings of other metals are identified. Thanks to quality cleaning of aluminum before melting, the rejection rate is reduced by 60 to 80%. The storage temperature for the raw material is controlled, about 70 degrees Fahrenheit, to avoid condensation, which can cause microbubble explosions if it gets into the molten metal. After cleaning from moisture and impurities, the aluminum is fed into large melting furnaces. These can be gas or induction units that heat the metal to approximately 1,220 degrees Fahrenheit. A stable melting temperature is maintained in these furnaces thanks to automated control systems, which prevents overheating and preserves the homogeneity of the future alloy. Furnaces typically have a volume of 5 to 10 tons, and one such furnace can produce up to 300 or even 500 cast cylinder heads per shift. One shift lasts 8 or 12 hours. The production flow is set up so that the molten metal is continuously supplied for casting, so even 15 or 20 minutes of downtime can cost the enterprise thousands of dollars due to lost pace and cooling of the material. Alloying elements are added to the molten aluminum, primarily silicon and magnesium. These elements increase the strength, heat resistance, and wear resistance of the finished part, making it suitable for operation under high pressure and fluctuating temperatures in the engine. As you can see, magnesium doesn't just improve human strength and wear resistance, but aluminum's too. After adding impurities, the alloy necessarily passes through a ceramic filtration system. Special porous filters capture oxides, microscopic particles of slag, and residual impurities. Without this filter, slag could get into the mold, form microcavities in the part's structure, and reduce its lifespan by tenfold. Filtration usually occurs in the ladle or holding furnace, where the molten metal is transferred from the main furnace. This is an intermediate stage where the metal is again stabilized by temperature and checked for chemical composition using spectrometers to precisely match tolerances. After cleaning and filtration, the molten aluminum goes to the casting shop, where it is poured into molds, a key moment when hot metal turns into a specific part, the cylinder head. This process must be extremely precise because the mold is complex, with numerous channels and cavities, and the engine's performance depends on the casting quality. Most often, gravity die casting or high-pressure die casting are used for head production. In the first case, the molten metal flows by gravity into a metal mold that can withstand several thousand cycles. In the second, the molten metal is injected under pressure up to 10,000 psi, ensuring precise filling of even the smallest channels. The mold, made of high alloy steel, is preheated to 400 degrees Fahrenheit or more to avoid thermal shock. The metal is supplied from a ladle or through an automated continuous feeding channel. A venting and gating system ensures air displacement, otherwise voids will form. The metal cools in the mold for 30 seconds to 1.5 minutes, after which the mold opens and the casting is sent on for further processing. Modern lines are equipped with sensors for temperature, pressure, and filling. The control system monitors the volume of molten metal, feeding speed, mold temperature, and metal temperature in real time. A deviation of more than 2%, and the machine automatically rejects the blank or adjusts the parameters. One casting station produces 40 or 60 heads per hour, depending on the technology. After the casting and cooling of the metal are completed, the next stage begins, removing the head from the mold. If sand casting was used, the mold is broken. It's a single-use structure made of a sand clay mixture, so it's simply broken apart to get the casting. In the case of die casting, a metal mold is used, which automatically opens, and the part is ejected by special pushers. At this stage, the so-called gray or rough blank is obtained, an unprocessed head with gates, risers, and irregularities. Its weight is 10 to 20 pounds, depending on the engine type and design. Almost immediately after removal, the heads are often sent for heat treatment. This typically includes quenching and tempering. The process involves heating to 1000 degrees Fahrenheit, holding at that temperature, and controlled cooling. This strengthens the metal structure, increases hardness, wear resistance, and thermal stability, critical parameters for operation in the engine's hot zone. After heat treatment, the cylinder head proceeds to the computer numerical control machining stage. The head is secured on a fixture in a multi-axis machining center. A computer program precisely sets the coordinates, speed, and order of processing. Machining includes milling the mating surface to the engine block, drilling holes for bolts and other parts, boring channels for coolant and oil, forming valve seats and guides. One machining center can complete a full cycle in 10 or 25 minutes. It all starts deep underground and ends up in your stove. Geologists hunt for gas, drilling rigs pierce the Earth's crust, and an explosive cocktail of gas, oil, and water erupts from the depths. Next, separators that stratify everything down to the last drop. Compressors that push fuel through pipes stretching 300,000 miles. And finally, the gas is cooled to negative 260 degrees Fahrenheit, turning it into a liquid to be transported across oceans. But how does it not explode? And how is it made safe for your kitchen? Watch and find out how gas really works. It all begins with geologists searching for true treasures underground, natural gas deposits. And no, they don't walk around with shovels. They use seismic waves to understand where gas is hiding beneath the earth. Once a location is found, well drilling begins. Imagine a drilling rig that can reach depths of over 10,000 feet. The well diameter is usually between 8 and 30 inches, and drilling takes weeks. After drilling the well, steel pipes are installed to reinforce the walls and prevent the well from collapsing. Then comes the magic. Under pressure of hundreds or even thousands of pounds per square inch, gas, along with oil, water, and a bunch of impurities, rushes to the surface. For this, special valves, Christmas trees, are used to control the flow and pressure. When gas, oil, and water erupt from the Earth's depths, they resemble a dirty cocktail with millions of particles of sand, salt, and other surprises. To separate this mixture into pure components, engineers use separators. The mixture, under pressure of up to 500 psi, enters the separator through an inlet nozzle. The first task is to reduce the flow velocity so that gravity can take effect. An inlet deflector, a baffle that breaks up the stream and slows down the movement, is used for this. Imagine sharply braking in a car. Heavy particles like sand and clay immediately fall to the bottom, while lighter ones continue to move. In the separator, the mixture separates into 3 layers. The bottom layer, water and sand. These are the heaviest components. Water with salts and fine particles settles first. Oil is lighter than water, but heavier than gas, so it floats in the middle. Methane and other light hydrocarbons rapidly rise to the top. To speed up the process, separators sometimes have inclined plates or cyclone modules installed, which increase the settling area. For example, plates angled at 45 degrees cause oil droplets to coalesce and fall down faster. If oil and water form an emulsion, demulsifiers, chemical substances that break the bond between droplets, are added to the separator. Sometimes, vibrating screens are used to filter sand from the bottom layer. The gas, meanwhile, passes through wire mesh mist eliminators that collect residual liquid droplets. Float-level sensors monitor the thickness of the oil and water layers. If there's too much oil, a valve opens and it flows into a collection tank. A gas valve at the top regulates the pressure so that the gas doesn't exit too quickly. The ideal pressure is between 100 and 300 psi for effective separation. A sand dump valve periodically opens to remove sediment from the bottom. A typical vertical separator for gas fields is 20 to 40 feet tall. That's like 2 or 4 giraffes stacked on top of each other. The diameter is 4 or 5 feet, roughly the diameter of a circus ring, and it's capable of processing up to 10,000 barrels per day. A separator is a complex device where physics, chemistry, and mechanics work together to create 3 separate streams. After all, if gas contains liquid droplets, it can damage pipelines through corrosion or hydraulic shock. And 1% water and gas reduces its heating value by 5, or even 7%. That's like adding gasoline to your latte. Oil from the separator is sent to storage tanks, water is purified or re-injected into the formation, and gas heads to dehydration units. Some gas components, propane, butane, ethane, can be separated out. To do this, the gas is cooled to 150 degrees Fahrenheit, and these components condense. They are collected in special tanks and sold separately. For example, propane for grills or butane for lighters. Clean gas isn't ready for its journey yet. It needs to be compressed to a pressure of 800 or even 1,200 psi to be pushed through mainline pipes that stretch for thousands of miles. Compressor stations, true giants with engines producing thousands of horsepower, are used for this. Gas moves through mainline pipelines with diameters ranging from 24 to 48 inches. They run underground at depths of 3 to 6 feet, and their length can reach thousands of miles. Compressor stations are located every 50 to 100 miles to maintain pressure. When more natural gas is extracted than is currently needed, it isn't just vented or left idle. This valuable resource is stored in special underground storage facilities, which can be imagined as huge banks for gas. The most common types of such storage are depleted oil or gas fields, as well as salt caverns, located at depths of up to 3,000 feet underground. Depleted oil fields are cavities left after oil or gas extraction. They have natural geological barriers that prevent gas from escaping. Gas is injected there under pressure through special wells, where it is stored in porous rock, filling the voids previously occupied by oil or water. A single well can produce up to 10 million cubic feet of gas per day. Salt caverns are artificially created cavities in salt formations. They are formed by dissolving salt with underground water, creating large voids that are ideal for gas storage. These caverns have high integrity and allow for rapid injection and withdrawal of gas, making them very effective for regulating supply. Underground gas storage is very important for the stability of the energy system. In winter, when gas consumption increases due to heating, additional gas is withdrawn from these storage facilities to meet consumer needs. Similarly, during peak load periods or emergencies, these underground banks help prevent supply interruptions. Storing gas underground is also economically advantageous, as it allows for balancing production and consumption, reducing costs for surface transportation and storage. It's a reliable and safe way to ensure that gas will always be available when it's needed most. The length of gas pipelines in the United States is over 300,000 miles. Before gas reaches your home, it undergoes another check for purity and pressure. At distribution stations, the pressure is reduced to 0.25 psi, which is safe for home stoves and boilers. For safety, a special odorant, mercaptan, is added so you can detect a gas leak. At all stages, from the well to your kitchen, gas is monitored by pressure, temperature, and composition sensors. In case of an emergency, valves shut off the flow in seconds. Personnel undergo training, and systems automatically record the slightest deviations. Besides homes, gas is supplied to power plants, factories, and chemical plants. For industrial consumers, the pressure and volume are higher. Pipes with diameters up to 48 inches and pressures up to 1,500 psi are used here. Gas can be liquefied. It's cooled and transported by tankers across seas. First, the gas is compressed, meaning it's made very dense, like when you squeeze the air in a balloon. It becomes smaller in volume, but warmer. Then, this warm compressed gas is passed through special coolers. After that, the gas is passed through special devices, expanders, which allow the gas to expand and cool down even more, like when you let air out of a balloon and it becomes cold. Thanks to this, the gas cools down significantly, to about -260 degrees Fahrenheit. When gas cools to such a low temperature, it turns into a liquid, like water, but very cold. This liquid gas takes up about 600 times less space than in its gaseous state, so it can easily be stored in special tanks and transported by ships. Imagine a machine that can withstand the blast of a high-explosive device, endure fire from automatic weapons, and keep rolling even with shot-through tires. This is the legendary Hummer, designed for the most dangerous missions. From operations in the Persian Gulf to modern combat zones, over 280,000 armored Hummer vehicles have become an essential part of the United States Army. How do these machines go through their testing? Which materials protect the crew? And why do they produce 70 of them per day? Let us find out. To understand why the Hummer became synonymous with invincibility, one should first look back at its history. In the 1980s, the American automobile company called A.M. General unveiled a modified Hummer that was initially developed for the civilian market. However, the troops quickly recognized its advantages for modern warfare, especially on the front lines, where soldier protection is paramount and armored vehicles became critically important for safety. A true breakthrough came after the Hummer became the main transport vehicle for the United States military during operations in the Persian Gulf at the beginning of the 1990s. Since the year 1893, over 280,000 Hummer units have been manufactured. But how can one ensure that this off-roader not only endures harsh conditions, but also provides protection in the most hazardous situations? What exactly sets the military armored Hummer apart from civilian models? Let us see how the armored components are constructed to turn these vehicles into a genuine steel shield on wheels. Military Hummer vehicles use specialized armor materials, including composite armor that combines steel plates with ceramic inserts. These materials can withstand shots from a variety of weapons, including automatic rifles and sniper rifles. Moreover, by incorporating composites, these vehicles are not only armored, but also relatively light for their size. The production rate is around 70 vehicles per day. A key structural element of the armored Hummer is the concept of plus armor. This means that multiple layers of protection are added onto the vehicle, enabling maximum defense in a wide range of combat scenarios. There are also additional design modifications, such as reinforced suspension and strengthened tires, allowing the vehicle to keep moving even if one of the tires has been damaged. Another important aspect is the strengthened floor and roof. In military Hummer vehicles, the floor is structurally protected against blasts. Special materials are used to absorb the shockwave, which reduces risk to the crew if the vehicle encounters a minefield or an explosive device. However, armor is only one part of the overall safety level. Each high-mobility multi-purpose wheeled vehicle, commonly known as the Hummer, consists of over 5,000 parts. Combat Hummer vehicles must not only be protected, they must also be real beasts capable of moving through absolutely any conditions. How is this kind of mobility achieved? In order to preserve high off-road capability and endurance, military Hummer models are equipped with a powerful diesel engine. This engine can generate substantial power that lets the vehicle easily travel through desert sands or mountainous routes, even if there is no road at all. A specialized transmission and adapted rear wheels ensure constant stability in the most extreme conditions. Many modern military Hummer vehicles integrate intelligent control systems that allow the engine and transmission to adapt to the terrain. This significantly boosts maneuverability and endurance during large-scale strategic movements. Armored versions receive steel that is 1/2 inch thick, along with bullet-resistant glass that is 1.5 inches thick. Besides armor, electronic safety systems are vital, such as sensors that detect mines and explosive devices, along with systems designed to remain fire-resistant. They add another layer of protection for the crew, which is particularly critical in combat situations. What else is worth mentioning when talking about armored Hummer vehicles? There are several technical considerations to bear in mind. Military Hummer versions often feature specialized camouflage coatings that help them blend into the environment. This is crucial for enhancing survivability on the battlefield, where every detail can make a difference. Interestingly, the Hummer is not a static vehicle. Its design allows modifications based on mission needs. These can include additional weapon systems, medical equipment, or other specialized modules, depending on the task at hand. A military Hummer can carry up to 2,500 pounds of cargo or tow up to 7,500 pounds. Producing armored Hummer vehicles is a complex and lengthy process that demands highly skilled engineers and advanced technology. Everything starts with meticulous planning. Engineers account for every aspect, from improved mechanical components to resilience during blasts. Multiple prototypes are built, each undergoing a battery of tests. They are dropped from heights, fired upon, and examined for endurance in different conditions. Previously, AM General, the company that originally created the legendary Humvee, was in charge of production. However, in the year 2020, the license to manufacture new military vehicles was granted to Oshkosh Defense. As a result, combat Hummer vehicles are gradually being replaced by the Joint Light Tactical Vehicle, a more modern armored off-road vehicle. Therefore, military and civilian versions are produced separately, using different factories, technologies, and even materials. The body and armored panels are cut using laser or plasma machines, and then they are welded by robots and highly qualified specialists. Precision is crucial, because all seams must be airtight to enhance blast resistance. The Hummer is built on a robust steel frame, designed to withstand high loads. The chassis and engine are assembled separately, then tested for functionality. Only after that are they joined with the body. Once the main parts are put together, the vehicle is fitted with armored panels and additional protection. This stage is time-consuming because every component must be installed with the utmost precision. The interior of a military Hummer is nothing like that of a civilian vehicle. Everything is dedicated to functionality. Some models have air conditioning, which is essential in desert conditions. After assembly, the vehicle is painted with special scratch and corrosion-resistant paints. Several options are employed: desert camouflage for sandy regions, woodland or urban camouflage for the respective environments, and anti-radar coating to reduce visibility on radar systems. This is no ordinary paint. It is formulated to withstand heat, freezing temperatures, and the impact of blasts. The high-mobility multi-purpose wheeled vehicle is not produced in the same way as mass-market civilian cars. It is manufactured in relatively small batches, so fully automated production is impractical. At the same time, certain processes, such as welding and painting, are streamlined by a conveyor system for speed and consistency. Each high-mobility multi-purpose wheeled vehicle is equipped with a 396 cubic inch diesel engine that outputs 190 horsepower. This powerful diesel engine is engineered to operate under extreme conditions. The transmission is a 4-speed automatic adapted for off-road use. The vehicle has permanent 4-wheel drive and automatic differential locks. It accelerates to 37 miles per hour in approximately 17 seconds. It is slow, but speed is not the main goal for the military. For military transport, the priorities are off-road performance, reliability, and endurance. The high-mobility multi-purpose wheeled vehicle is not designed for swift maneuvers, but for traveling over any type of terrain. It has a high ground clearance of 16 inches, which allows it to clear rocks, ditches, and logs. Full-time 4-wheel drive and differential locks prevent it from getting stuck in mud or sand. The engine and fuel system are protected to withstand fire and blasts. There is minimal onboard electronics, meaning fewer things can break down in the field. It can continue moving on punctured tires. Special inserts allow driving even after the tire has been hit by a bullet. Its payload capacity allows transporting ammunition, injured personnel, and weapons ranging from machine guns to anti-missile systems. It may not be the fastest ride, but it will get you where others simply cannot go. The standard military high-mobility multi-purpose wheeled vehicle initially did not have armor, but since the year 2000, most models have received protection against small arms fire and shrapnel. Configurations vary, from soft body transport versions to the most widespread ones, capable of withstanding a high explosive device blast of up to 13 pounds. There are models with protection systems against chemical, biological, and nuclear weapons. Assembling a single high-mobility multi-purpose wheeled vehicle takes from 3 to 5 days, depending on the armor. At the AM General facility, where they build the high-mobility multi-purpose wheeled vehicle, there can be up to 3,000 workers in one workshop. However, only about 25 or 30 individuals work on assembling a specific vehicle at any given time. These include welders, mechanics, electricians, and armor specialists, each carrying out their tasks at each stage of the production line. The more complex the version, the more time and personnel are required. Before they are shipped, all high-mobility multi-purpose wheeled vehicles undergo 310 miles of test trials across off-road terrain, water, and dust. You already know how the Hummer is painted, but allow me to elaborate on the special matte paint known as chemical agent-resistant coating, which has several important properties. It does not reflect infrared light, making it harder to detect the vehicle with thermal imaging and night vision equipment. It resists chemical attacks. Its formulation makes it easier to wash off hazardous substances following chemical contamination. It withstands scratches and corrosion, enduring impacts from branches, sand, rain, sun, and aggressive liquids. The matte finish eliminates glare, which is critical for battlefield camouflage. The painting process involves multiple layers that are applied to the aluminum body and armored panels. Imagine this. Every single year, all around the world, over 70 million automobiles are manufactured, and each one of them demands high-technology glass. From the broken flask with nitrocellulose that accidentally revealed laminated glass, to the powerful hydrophobic coatings, the history of this material is truly astonishing. Today, we are going to learn how glass becomes ultra-strong, safe, and prepared to protect us from wind, rain, and the dangers of the road. Please get ready for a journey into the realm of advanced modern technology. Thousands of short tons of glass scrap are recycled in order to create crystal-clear windows for automobiles. It is not only about safety, but also about saving precious resources. And that is just the beginning. The history of automobile glass production is closely linked to the development of the automobile industry, which emerged in the late 19th century. The glass used in today's automobiles has undergone a long path of improvements that have made it safer, stronger, and more functional. When the very first automobiles began to appear, they were initially not equipped with any glass at all. The open body design offered only partial protection to passengers, while dust, wind, insects, and other hazards made traveling extremely uncomfortable. Later on, when automobiles became faster, the need for driver and passenger protection emerged. Windshields were first made from ordinary window glass, which, although it provided some degree of protection, had a serious drawback. In accidents, it would shatter into large, sharp fragments that resulted in numerous injuries. The first groundbreaking discovery in the field of automobile glass was the creation of laminated glass. This happened by chance. In 1903, a French chemist named Edouard Benedictus accidentally dropped a flask coated with nitrocellulose. The glass cracked but stayed in one piece, thanks to the thin layer of plastic. This accident inspired the scientist to develop a multi-layered glass, which later became the basis for triplex. By the 1910s, laminated glass was already being used in premium-class automobiles. Its construction consisted of 2 layers of glass with a thin, transparent film in between them. In the event of impact, the glass did not scatter, and cracks remained on the film. In the 1920s, laminated glass began to be widely used in the production of windshields. Its main advantage was increased safety. Even in serious accidents, the fragments did not fly apart, but remained embedded in the polymer layer. The next stage in the evolution of automobile glass arrived in the 1930s, when the technology for making tempered glass was patented. This material was produced by heating the glass to high temperatures followed by a rapid cooling. As a result of such a process, the glass became stronger, and upon breaking, it would fracture into small pieces with dull edges, minimizing injuries. By the middle of the 20th century, tempered glass was being used for the side and rear windows of automobiles. It was less expensive to manufacture compared to triplex, and provided a sufficient level of safety for those parts of the vehicle. In the 1950s and 1960s, automobile glass became even more advanced thanks to ongoing technological progress. During this time, several important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and more durable. Mass production. The automation of manufacturing processes drove down the cost of automobile glass, making it more affordable for a wide range of consumers. Coatings for sun protection. Special coatings that blocked ultraviolet rays and reduced the heating of the automobile cabin were used for the first time. One of the most significant technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, enabled the manufacturing of perfectly smooth glass by allowing molten glass to spread across the surface of molten tin. Through this method, the glass became more uniform, stronger, and better suited to mass production. Even today, the float method remains the foundation of automobile glass manufacturing, ensuring precise dimensions, a smooth surface, and high quality. In the second half of the 20th century, automobile glass underwent even more changes aimed at improving both safety and comfort. In the 1960s, heating filaments began to be installed in the rear window of automobiles, preventing condensation and freezing. In the 1980s, glass was introduced with special metallic coatings that reflected sunlight and reduced heat buildup inside the vehicle. Glass with ultraviolet protection. With the introduction of new technologies, automobile glass began providing virtually complete protection from harmful ultraviolet radiation. And now, we enter the modern period of automobile glass production, which we will discuss at this very moment. We shall start with the glass used in automobiles. Automobile glass is divided into several types, depending on its purpose and manufacturing technology. Windshield. This is usually multi-layered glass composed of two sheets of glass with a polymer film between them. This design ensures that, if damaged, the glass does not break into sharp fragments. Side and rear glass. Most often, this is tempered glass, which, upon impact, fractures into small, blunt-edged pieces that reduce the risk of injury. Panoramic roofs, or other special types of glass, often use laminated or tempered glass with specialized coatings for protection against ultraviolet radiation. The main components of glass are natural materials, which are mixed in certain proportions to achieve the desired properties. Quartz sand is the principal element in glass, giving it transparency. It must be extremely pure and contain minimal impurities. Soda is added to lower the melting temperature of glass. Lime improves the mechanical durability and chemical characteristics of glass. Additional additives. These are used to adjust color, transparency, resistance to ultraviolet light, and other properties. The raw materials are cleaned, dried, and ground to a uniform state. It is crucial to eliminate as many impurities as possible, as they can affect the quality of the glass. After preparation, the raw mixture is poured into special furnaces for melting. This stage includes a few important steps, so let us review them together. Melting temperature. To create molten glass, a temperature of about 2,732 degrees Fahrenheit is used. Throughout the melting process, the raw materials transform into a uniform, viscous liquid. Homogenization. The molten glass is stirred to distribute components evenly. This is important for preventing air bubbles or other irregularities in the finished product. The furnaces for melting glass are equipped with modern systems for temperature control and process automation, which guarantee the high quality of the final product. After melting, the molten glass proceeds to the forming stage, most commonly performed using the float method in modern manufacturing. Feeding the molten glass. The liquid glass flows from the furnace onto a bath of molten tin. Due to the high density of tin, the molten glass spreads out uniformly across its surface. Under its own weight, the glass forms a perfectly even and smooth surface. Gradually lowering the temperature makes the glass grow solid. By the time it leaves the tin bath, it is ready for further processing. The float method allows the production of glass sheets with precise geometric parameters and a very high quality finish. Once it is cooled, the sheets of glass are cut to the sizes required for automobile manufacturing. Automated cutting machines ensure accuracy, and to prevent chips or cracks, the edges of the glass are polished. Every sheet is checked for defects, such as microcracks, bubbles, or other damage. Next, to ensure the strength and safety of automobile glass, it undergoes the process of tempering. The glass is heated to a temperature of around 1,112 degrees Fahrenheit. Then the surface is quickly cooled by air jets, while the inner layers cool more slowly. As a result, stress is created, which greatly increases impact resistance. Tempered glass, when broken, shatters into small, safer fragments, minimizing the risk of injuries. After that, for the windshield, a triplex construction is used, which is a combination of glass and polymer film. Its fabrication involves several steps. Layer bonding. A polymer film is placed between two sheets of glass. The construction is placed into a vacuum press to remove air bubbles. Then the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure, ensuring a strong bond between the layers. Triplex has high impact resistance, and if damaged, the fragments stay attached to the polymer film, thus providing safety for the driver and passengers. Afterward, to enhance the properties of automobile glass, various coatings are applied. Anti-glare coatings reduce glare from the sun or from other vehicles' headlights. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings allow water to bead and roll off the glass surface. Heating elements. Thin heating filaments can be embedded in the windshield, making it easier to remove ice or condensation. To achieve the required shape, special thermoforming equipment is employed. The glass is heated to a temperature at which it becomes pliable, and it is then molded according to specified parameters. And here we arrive at the final stage. During this stage, each piece undergoes a thorough inspection. The transparency is tested, and any defects are identified. Next, the glass is tested for impact resistance and durability under load. Compliance with standards, the accuracy of dimensions, the shape, and other parameters are verified. Then the finished automobile glass is packaged in a manner that prevents damage during transportation. It is delivered to automobile factories or service centers, where it is installed in vehicles. The production of automobile glass is a high-technology process that brings together physics, chemistry, and engineering. Thanks to advanced technologies and strict quality control standards, automobile glass ensures safety, comfort, and longevity. And just imagine how many stages automobile glass must go through so that we can watch over road safety and admire wonderful vistas along the way. I find it remarkable. Do you also think so? Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress. So there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. Every year, over 150 million carats of diamonds are mined worldwide. But did you know that some mines are so deep that the temperature inside exceeds 110 degrees Fahrenheit, and powerful explosions can cause seismic tremors felt up to 50 miles away? Diamond mining isn't just digging. It's a full-scale scientific operation that starts with satellite analysis and can last for decades. How are these precious stones found? How do drilling rigs reach depths of 10,000 feet? And what happens to diamonds after they're mined? Let's break it down together. Diamonds form deep beneath the Earth's surface and are brought up through volcanic processes that create kimberlite pipes. These pipes, made of ancient igneous rock, are the primary sources of diamonds and can reach depths of over 10,000 feet, with temperatures inside the mines exceeding 110 degrees Fahrenheit. To cool these environments, powerful ventilation systems compress air. In some mines, the air is so pressurized that if a door between compartments is suddenly opened, the wind force can knock a person off their feet. Sounds dangerous, right? Before mining begins, geologists conduct extensive exploration that can last for decades. The process starts with analyzing satellite images and aerial photography. This is followed by field studies, where geologists collect rock samples for chemical analysis. Special attention is given to the presence of indicator minerals like garnets, ilmenite, and pyrope, which suggest the potential presence of diamonds. If the exploration yields positive results, detailed surveying begins. Drilling rigs create boreholes up to 10,000 feet deep, extracting core samples, cylindrical sections of rock. These samples undergo thorough laboratory analysis to assess the diamond content in the rock. Geophysical methods like magnetic surveys, electromagnetic scanning, and gravimetry are used. Open pit mining is employed when the deposit is relatively close to the surface. Underground mining is used if diamond-bearing rocks are located at significant depths. Mine shafts are constructed, allowing workers and equipment to descend. Mining begins with drilling boreholes into the kimberlite rock. For this, massive drilling rigs over 50 feet tall are used. Each borehole can reach lengths of 2,000 feet, and a single mine may have tens of thousands of such holes. After drilling, explosives are placed in the boreholes, and the detonation occurs under strictly controlled conditions. Some diamond mines use such powerful explosives that underground blasts can trigger minor seismic tremors detectable over 50 miles away. First, vertical shafts are dug, reaching depths of over 10,000 feet. The diameter of the main mine shafts often exceeds 20 feet. Additionally, horizontal tunnels are constructed, stretching for several miles. After the explosion, the rock in the mine breaks into pieces of various sizes, from large boulders to fine gravel. Powerful loaders with buckets lift the debris and transport it to central transfer points. Here, massive dump trucks, each capable of carrying over 250 tons of rock, load the extracted material and deliver it to the main tunnels. In some mines, instead of trucks, specialized electric trains running on tracks tens of miles long are used, capable of transporting over 500 tons of kimberlite rock per trip. The main tunnels are equipped with conveyor systems that start at depths of several thousand feet and extend to the surface. The length of these belt conveyors can exceed 15 miles, with belt widths over 6 feet. Some systems have multi-level structures, allowing simultaneous material transport from different parts of the mine. Before being placed on the conveyor, large rock fragments pass through crushing stations, where massive steel rollers over 20 feet long break the debris into fragments no larger than 3 feet in diameter. The crushers operate with compressive forces of tens of thousands of pounds per square inch and can process over 10,000 tons per hour. After initial crushing, the material is loaded onto the main conveyor belts, which transport it to the washing system. In some sections, the conveyors pass through special grottos equipped with giant sieves with holes of various sizes. During transport, smaller rock particles are sifted and directed to separate processing lines, while larger pieces move to the next stage of crushing. The newest mines are equipped with automated control systems that analyze the rock composition in real time and adjust conveyor speed and crushing intensity. As the future diamonds approach the surface, they are fed into special bunkers where the rock accumulates, ready for further processing. The capacity of these bunkers can exceed 100,000 tons, and their structure allows for even material distribution to washing and sorting facilities. In mines located in deep regions, transporting the rock can take several hours, with annual extraction volumes reaching millions of tons. When I was a kid, my family loved going to the beach. It didn't happen often, my dad rarely had time off, but when it did, everyone was thrilled and happy. Diving underwater to find seashells, crabs, or even clams, I never imagined that diamonds could be mined from the sea. Deep sea diamond mining is one of the most complex and technologically advanced methods in the mining industry. Mines are located where kimberlite pipes or alluvial deposits lie beneath the ocean floor at depths exceeding 500 feet. Geologists begin by conducting surveys using underwater drilling rigs. These rigs are stationed on specialized offshore platforms or vessels equipped with computerized navigation systems for precise positioning over potential deposits. Once diamond-bearing deposits are confirmed, the construction of an underwater mine begins. This is a complex process involving the creation of sealed tunnels or the use of massive drilling capsules operating under high pressure. One method involves using giant seabed drilling complexes, which can exceed 200 feet in length and weigh over 5,000 tons. These complexes are equipped with diamond-tipped drills capable of cutting through even the hardest rock. During drilling, a specialized hydraulic system creates a water flow under pressures exceeding 3,000 pounds per square inch, washing out small rock particles and diamonds into special reservoirs. Another method uses giant underwater vacuum systems that can descend to depths of up to 1,000 feet and suck up hundreds of thousands of cubic feet of rock per hour. The material is then brought aboard a vessel or platform for initial processing. Special underwater crushers can process up to 50 tons of kimberlite rock per hour. Powerful pumping systems are used to transport the rock to the surface, capable of moving up to 1 million gallons of water per day. Streams of enriched rock are directed through pipelines that can stretch for several miles. The material then enters large sorting tanks, where it passes through gravity separators. Heavier diamonds settle at the bottom, while lighter particles are washed away and returned to the sea. Remotely operated underwater vehicles play a crucial role in deep-sea mining, operating at depths of up to 10,000 feet. They are equipped with manipulators that can precisely collect large diamonds directly from the seabed. Their high-resolution cameras allow operators, located hundreds of miles away, to control the process in real time. Deep-sea mining is so complex and costly that only a few countries in the world have the necessary technology. It can cost hundreds of millions of dollars, and the full mining cycle can take over 10 years. Despite the challenges, this method yields millions of carats of diamonds annually, supplying the global market with precious stones hidden in the ocean's depths for billions of years. On the surface, the extracted rock is crushed in processing plants, where massive steel jaws over 20 feet long break the stones into fragments smaller than 2 inches. Each plant can process over 10,000 tons of material per day. After crushing, the rock passes through a series of washing tanks filled with water and chemical reagents. Diamonds, which have high density, settle at the bottom, while lighter minerals are washed away. Once the material is on the surface, specialized X-ray separators are used to identify diamonds based on their ability to fluoresce under ultraviolet light. Magnetic separators work by exploiting differences in the magnetic properties of materials. Diamonds are non-magnetic, while most minerals in kimberlite rock have weak magnetic properties. In these systems, the rock is fed onto rotating drums over 20 feet long, which generate strong magnetic fields exceeding 10,000 Gauss. Magnetic mineral particles stick to the drum's surface and are removed into a separate container, while diamonds and non-magnetic rock residues move forward. X-ray systems are used in the next stage, when the rock is already significantly purified. These systems rely on diamonds' unique ability to fluoresce under X-ray radiation. The stones enter a special tunnel where they are exposed to X-rays with energies of up to 200 kiloelectron volts. The diamonds begin to glow, and highly sensitive optical sensors instantly detect their location. The system then activates a high-speed air jet operating at pressures exceeding 100 pounds per square inch, which literally blows the diamonds out and directs them into a collection container. The cleaned diamonds are sorted by size, quality, and color. The sorting process is fully automated and managed by operators in specialized control centers. Each operator monitors dozens of X-ray systems using high-resolution computer panels. Modern systems use machine learning algorithms that can adjust equipment parameters in real time for maximum efficiency. If malfunctions or deviations occur, operators can manually change settings or redirect material flows for reprocessing. A single system can process up to 20 tons of material per hour with precision that detects even the tiniest diamonds smaller than 1/10 of an inch. At large diamond mines, dozens of such systems operate simultaneously, extracting hundreds of millions of carats annually. After sorting, the diamonds are sent for cutting, where artisans use lasers and mechanical tools to transform them into precious gemstones. Once cut, they enter the market, sold as part of jewelry or used for industrial purposes.